Hey everybody. Today we're talking about controlling the family-wise error rate when running multiple statistical inferences. When you're running more than one statistical test, the probability of getting at least one false positive, or type 1 error, increases rapidly, meaning that some random patterns in your data are likely to appear to represent real trends if you just look at the p-values. There are many different ways of handling that problem and correcting for it. The two I'm going to talk about today are the Bonferroni correction and the Holm correction. And these are old and relatively simple methods. And they both work exactly the same way. By controlling the family-wise error rate, FWER, the probability of getting at least one false positive, at a chosen significance level, typically 0.05. They are simple in the sense that neither one of them makes any assumptions about the sorts of tests that you're running. In order to apply these corrections, all you need is just a sequence of p-values. Now, before I go into those methods, I just want to say very directly, data dredging is bad statistical practice. I have a whole video on data dredging. I'll throw a link up top. No correction will fully account for the problems with data dredging. By data dredging, I mean running an exploratory analysis, for instance, getting some visualizations from some data, finding some apparent trends, and then running a statistical test, or a small handful of tests, on the ones that appear to be interesting. That's a problem for a lot of reasons. First of all, you just lose clarity and focus when you combine exploratory and confirmatory analysis. The former being something where you're supposed to be generating your hypothesis. The second one's supposed to be where you test or confirm those hypotheses. If you barrel ahead and apply these procedures anyway, even if they were statistically valid in that situation, you'd still be sacrificing a great deal of statistical power, so it's not in your best interests anyway. I always say, when you're running statistical inference tests, you should be writing down your hypotheses before you look at the data, preferably before you even collect your data. If you don't do that, if you just find some trends and then run a test and maybe even do a corrected p-value afterwards, the fact that you've chosen the thing that you're testing based on a visually apparent trend almost guarantees that you're going to get a significant result, and you should view the statistical inference that you've run with extreme skepticism. Okay, enough with the disclaimers. Let's now assume that you have k statistical tests that you've run using best statistical practices, and you're just worried about false positives. If you run k independent statistical tests, your family-wise error rate is given by this formula. And I talk more about this in the data dredging video, so I recommend watching that if you haven't already. For now, all you really need to know is that for small k, this is just a little bit less than or equal to k times alpha, the number of tests times the significance level. And as k gets larger, it gets closer and closer to 100%, so certainty of getting at least one type 1 error. The Bonferroni correction is super simple. It just says, take the p-values that you have and multiply each one by the total number of tests, k. And that works because the family-wise error rate is never greater than k times the significance level of each individual test. And here's a line of math that shows that. I won't say too much about that. Equivalently, multiplying the p-values by k is the same as dividing the overall significance level of the test by that k. So if you have 5 tests at alpha equals 0.05, you can think of it as a cutoff for statistical significance of 0.01. Quick example, suppose we have these 4 p-values. Notice that these are all less than 0.05, and so individually each one would qualify as statistically significant when taken in isolation from the others. Applying a Bonferroni correction, we would multiply each of them by 4, and so the results would be 0.004, 0.020, 0.080, and 0.160. And if you're using a significance level of alpha equals 0.05 for the overall test, trying to control the family-wise error rate at 0.05, only the first 2 results would be considered statistically significant. The Bonferroni correction is old, it's well known, it's simple. People that deal with data will have heard of it. It doesn't rely on difficult math. And again, it doesn't make any assumptions about the sorts of tests being performed. It's also useful just for sort of a back-of-the-envelope mental model when you're planning a study or planning an analysis. If you have k tests at significance level alpha, the cutoff you're looking for each test is alpha over k. On the other hand, the Bonferroni correction is very conservative, and it sets a high bar for statistical significance. That means you're going to have higher probabilities of false negatives, or type 2 errors. To say that a little bit differently, some real patterns in your data may be overlooked as potentially just due to random chance because of those higher adjusted p-values. The Holm correction is a less conservative approach. It's also known as the Holm step-down procedure or the Bonferroni-Holm correction. Similar to the Bonferroni correction, it's attempting to control the family-wise error rate when you've got multiple tests at some overall level alpha, typically equals 0.05. However, it usually yields smaller adjusted p-values, and so that means you have less probability, lower probability of type 2 errors. In other words, greater statistical power. To say it in the sort of most technical terms possible, the Holm correction is uniformly more powerful than the Bonferroni correction. In practice, there's not a good reason to use the Bonferroni correction unless it's the only thing that people you're working with have heard of or will trust for some reason. The trade-off, of course, is that the Holm correction is slightly more complicated. It's not bad, though, so let's run through it really quickly. If you've got kp values, you arrange them from low to high. The smallest ones first, the highest ones last. Instead of multiplying the whole sequence by k, you only multiply the first one by k. You multiply the second one by 1 less, k minus 1, the third one by 2 less, k minus 2, and so on. You then identify the first adjusted p-value that's greater than your significance level, alpha. All p-values before that are considered significant, and all the others are not. If none of them are greater than alpha, then of course they're all considered significant. Now I'm going to do an example on this on the next slide, so that'll make it perfectly clear if this explanation isn't already. The last thing I want to say before I do that is that when you're reporting the p-values for this sequence of tests, it's standard practice to further adjust the p-values so that you get a non-decreasing sequence, so that each p-value is no smaller than the one that came before. That's the way that R's p.adjust function works. I'm going to show that function off in just a minute. Okay, example. Suppose we have these 5 raw p-values, starting with 0.005, then 0.011, and so on. Again, they're all less than that cutoff of p equals 0.05, and individually would be considered statistically significant at that level. First, let's look at the Bonferroni correction. Since we have 5 values this time, we multiply each one by 5, we get these values. Only the first result is considered statistically significant. With the Bonferroni correction, the others are not. Multiplying by 5, again, is pretty aggressive, pretty large correction. So we've set a rather high bar for statistical significance. Now let's do a Holm correction. We multiply the first p-value by 5. That's where the 0.025 comes from. We multiply the second one by 4, 0.044. The third one by 3, the fourth one by 2, and the fifth one by 1. And using the Holm correction now, the first 2 results are considered statistically significant at alpha equals 0.05, while the others are not. To report those adjusted p-values, you should make the sequence non-decreasing. So if you look at that fourth value, 0.070, it's gotten smaller than the one that comes before it. And using the Holm correction method, that shouldn't happen. We bump that up to 0.075, and then similarly for 0.045, we bump that up to 0.075 as well. Okay, let's actually see how to do this in R. The command that we're going to use is p.adjust. I've pulled up the help file. And p.adjust just needs 2 arguments. First, it needs a vector of p-values. And here I've already coded in a vector of 5 p-values from that last example. Secondly, we have to pass p.adjust the sort of correction method we want to use. And I will start with Bonferroni, which I think I've spelled correctly. And here you can see, there we go. I've gotten exactly the same result that I got by hand on that last slide. I've just taken these p-values and multiplied by 5. Pretty simple. Next, let's do it with the Holm correction. So we'll replace the word Bonferroni with Holm. And now you can see that we've multiplied by 5, by 4, by 3, by 2, and by 1, but then we've rounded upwards to make this sequence non-decreasing. That's the Holm correction. Now, if you read the help file, you'll see that there are other methods available. Again, I encourage you to read about all of this. There are 2 other methods included for adjusting the family-wise error rate. They make assumptions about the sorts of tests that are being run, independence, for example. The other 2 methods that are available here don't address the family-wise error rate. In other words, the probability of at least one false positive. Rather, they look at the false discovery rate, which is a less stringent criteria, which is both good and bad. I'll get to talk about the false discovery rate in an upcoming video. Once I have that video ready, I will put a link up top.